Well, okay, so let's continue with Birgit Rudloff, who is, has done quite a lot of work in multivariate and set-valued risk measures, and she's going to talk to us about dynamic programming for multivariate problems involving this.
Thank you very much. And thanks for the invitation. I'm happy to be here. And I will talk about some recent research. So this is part of it is a work in progress, which I will explain at the end. Part of it is research that have been over the last years, but there's some connection behind it, which I want to point out today. So I will basically talk about a few different applications, but to see a little bit the bigger picture behind it. So that's, let's say, the aim of the talk. So it will be about dynamic problems at the end, but they are of a multivariate nature and somehow involving risk measures. So I will start with an example to see where the multivariate nature in some problems involving risk measures will appear. So my starting point will be systemic risk, just as a motivation to, let's say, get the multivariate nature of the problems into it, which is based on a recent paper with my former PhD student, Zach Feinstein and Stefan Weber, on systemic risk measures. So systemic risk, you have a network of banks, they are all kind of linked to each other, and you want to measure the risk of the whole system. Yeah. This is just a picture of the Brazilian network, and just to make it a little bit more where I can explain things. Just a simple case where we say we have these 6 banks. So each node is basically a bank, and there are connections between them by just lending between the banks. Yeah. And then, of course, you can have also society as an additional node. And of course, there are links from each of the banks to society. And when we're talking about systemic risk, a lot of times we're actually interested in how possible defaults in the banking network affect the rest of the world, which is represented by society. So society is basically everything outside of the particular financial network you're looking at. But I mean, if you put society into the picture, it's just a network with one more node at the end. So a lot of the analysis doesn't change. But for systemic risk, it's important because this is most of the time what you're interested in, how the system of banks impacts society. Yeah. Okay, so these banking networks, we have seen a talk this morning also about banking networks existed for a long time. So the basic paper is the Eisenberg-Noe model for the lending between banks. There have been a lot of extensions for different, adding other type of implicit connections between banks. So there has been a lot of work in this field. But we stick for the talk just to the basic network. But a lot of the things that you see can also be done for more general, let's say, models. So let's say we have the D banks, and they are linked to each other, and each bank has some, let's say, a random endowment. So we have a random vector, a d-dimensional random vector. And we are interested in some impact function, which at the end will be something like how the D dimensions from the banking network impact society. So it's the impact of the d-dimensional network to the one-dimensional society. Yeah, a lot of times this is also called an aggregation function. But if you really think of an impact, I think impact function more gives an appropriate name to it. We will see in a second an example of what this impact function could look like. But there are very different examples in the literature. Yeah, but on a generic term, you can think just about this is a function modeling how the system impacts society. And it can come from direct network effects, like in the Eisenberg-Noe framework, but it can also include indirect spillover effects from the more, let's say, recent papers. And then from the risk measure point of view, we might be interested in regulating the D banks, and regulating would mean how much capital each of the banks, so we have a vector in RD, has to put aside in order to account for the systemic risk of the network. Yeah. So how much money for each of the banks is necessary to make the impact to society acceptable in a certain sense. Yeah. And this means when you have the random endowment vector of the banks and you add the capital charges for each of the banks and look afterwards at how this, let's say in the changed system, yeah, when you regulated the banks, how this impact to society would be, you want to make regulations such that the impact is acceptable in a certain sense. Yeah. That means in systemic risk measurement, we are actually trying to find vectors of capital charges such that after I changed the endowment, yeah, by adding this capital charges, I made the impact to society acceptable, where this, you can just think of an acceptance set of a regular scalar risk measure. Yeah. And this will be just my, let's say, one example of where a multivariate risk measure will pop up naturally because a banking system somehow is higher dimensional, which, I mean, has an influence basically on the risk measures, because at the end we want to know the vectors of capital of the D banks that make the system somehow acceptable. Yeah. So this is really, at the end, it comes out to be a risk measure where we look at the collection of vectors. So it's like a set-valued function. Yeah, for a given x, you basically, if let's say we just have two banks, yeah, bank 1 and bank 2, and the risk measure would basically give me a whole set. Yeah, and each point on the set would be a possible capital charge for each of the banks that would make the system acceptable. We're collecting all of the possible vectors. At the end, we are usually, for risk measures, we're interested in the smallest amount of capital that makes something acceptable. Here, the smallest amount would be basically something that is on this boundary, yeah, on the kind of efficient frontier. But it's easier to work with the whole set, so everything above would also be part of my risk measure. Okay, so this just as a, let's say, small motivation to see where naturally a multivariate function pops up when we talk about systemic risk. And I could also rewrite this, which I will use later on a little bit. So if I just, so remember this, oopsie. This is basically a one-dimensional acceptance set. Yeah, you can just think of value at risk, entropic risk measure, average value at risk, or something like this. I could also rewrite the risk measure in the following terms. If I collect all the random vectors where the aggregated vector is acceptable, yeah, in the one-dimensional sense, then I could also rewrite the risk measure in this terms of the collection of all vectors, such that when I add the vector k to the random vector x, I make it acceptable with respect to this, let's say, d-dimensional acceptable set. So we will see that this is a structure that is, let's say, a generic set-valued risk measure, and systemic risk measures are like a special case of this, where the acceptance set is generated by this impact function or aggregation function. Yeah. Okay. So okay, so this was my motivating example, just to see where naturally you want to regulate all the D banks, so you have somehow a higher dimensional risk measure appearing. And I will now give just one example what this aggregation function or this impact function, where this is coming from if you would choose a network model. There are very different examples in the literature, and kind of all of them use some aggregation function of one sort. I just want to give an example where you see how it can be extracted from a network model. Yeah. So to see this, let's just look at the basic framework of Eisenberg-Noe, where I have the banks, and the links between the banks are basically the lending between the banks. So I will look at the direct linkages by the interbanking liabilities. And as I said, it has been extended in various ways, but here we stick just to the basic framework just to see a little bit what an example of this lambda function could be. Okay, so let's say we have this D financial institutions, each has an endowment XI, and we can add society as an additional node to it. And we look at the liabilities between each of the banks. So the PIJ bar is a promise payment from bank I to bank J. That means the total liability of bank I is just the sum over the PIJs over all Js. Yeah, what I basically have promised payments to different, let's say, people in the network, and then you usually look at the relative liability. So from my total promise payment, I have maybe 70% goes to Johannes and 30% to Kostas. Sorry. And then in the network model, so as I said, we can add society to it. But what is important is basically what you're interested in is if now, let's say one bank is defaulting and you want to know now the defaulting bank cannot pay the promised payment to the other bank. And you want to know if this bank is also defaulting. Of course, to decide if this bank is defaulting, you need to know if this bank can now pay all of its promised payments or not. But you can only determine it. So if, I don't know, if he can pay, for example, all of the amount to this guy, it depends how much he's getting from the other. So it also depends how much he's getting from this guy. Yeah. But this depends on how much he's getting from this guy. So that you have these circles basically. So you can only compute the realized payment by computing a fixed point. So in mathematical talk, and it doesn't change if you add society to it. Yeah, it's just one more dimension in the network, basically. So to compute the realized payment, which are the P's without the bar, you basically solve a fixed point problem. And it's pretty straightforward. You basically look what you're really getting from the other guys, which is the percentage basically times the total realized payment. So this is how much you get from all the other banks. This is how much you have. So this is really what you get, what you have. And if you have enough, you would basically, this would be the amount you pay. Yeah. If you have enough money, you would pay what you have promised. So that you would choose the minimum of this two. If you have enough money, you would, the realized payment would be what you promised to pay. But if you don't have enough, you can just pay what you actually have. And then it would be smaller than the promised payment, and this would be your realized payment. Yeah. But the P, of course, appears on both sides of the equation. So here you have the vector of the P's, and here you have the vector of the P's, so it's a fixed point problem. You're looking for the P that makes this equation equal if you plug it in on both sides. Okay. And then you can, on the very mild assumptions, this fixed point is unique. You can compute it by just solving a linear optimization problem. So it's an LP. Yeah. Okay, so this maybe just as a background, how in the network model you can compute, from given the liability matrix, you can compute the realized payment. I think a lot of people know this stuff anyway, who worked on systemic risk. But how does it help us to calculate this impact function lambda? Yeah. So once we compute it, basically a fixed point, which would give me this vector P, I can look at the losses, of bank I, or the equity of bank I, which is basically, again, what I really get from the other banks, plus what I have. So this is what I, let's say, after clearing the system, what I really have, minus what I promised to pay. If this is still positive, the leftover would just be my equity. Yeah. If this is negative, it meant I couldn't pay my full promised amount and I defaulted. That means this quantity, the vector E, would be either my equity if it's positive, or it would be my loss after default if it's negative. Yeah. And if I'm really interested in the wealth of the society, I would just need to look at the zero component of this vector. Yeah. But the zero component still needs the whole realized payment vector from the equilibrium that I computed, yeah, in the fixed point problem. But the zero component would basically, if you take this, it would be like an aggregation function, like an impact function. After the possible chain of defaults in your network, it tells you how much did society lose because of these defaults in your network. Yeah. So how much you couldn't get back basically from the promised payments from the banks. Okay, so this just as one example where an aggregation function comes out of a network model and can be used in this definition of systemic risk measures. Yeah. But there are other possibilities. It's just one example how you could set up such an impact function. Okay, so again, coming back to our definition of this systemic risk measures, which we thought was the vector of capital regulations such that if I add the capital to my random endowment, it makes the impact to society acceptable. I think my picture is actually really hard to see, right? Anyway, now from the distance, it looks like white. Okay, let us compare this to a lot of the approaches that I've seen in the literature on systemic risk. Of course, I'm not the first one to talk about systemic risk measures, so there have been a lot of papers on that. But up to now, most of the papers used the following approach, that they looked at the aggregated risk, so they aggregated the vector x, yeah, applied an aggregation function to it, and then used a usual scalar risk measure applied to this aggregated risk. Which, if you write it out from the risk measure perspective, is just you're looking at the smallest amount of money, and this is now real valued, such that when you add this amount of money to the aggregated risk, it becomes acceptable. I mean, this is basically just using, okay, we have something d-dimensional, we somehow need to make it one-dimensional because we just know how one-dimensional risk measures work, and this is like the easiest way to set up systemic risk measure, right? But the drawback is that the interpretation is basically something like this. You aggregate first and then you add a real amount of money, which means you look at how X imposes certain defaults and chain of defaults in the system. And then after the chain of defaults happens, we want to know how much money do I need to bail out this defaulted system. So the interpretation would be that it's something like bailout costs. Yeah. After everything defaulted, you want to know how much money to inject into the system to make it acceptable again. Right? Whereas in contrast, our approach is something like you want to regulate such that the defaults do not even happen. Yeah. So that you first add the money and then make this changed system acceptable. Yeah. So from a regulatory point of view, the more natural thing would be to look at these kind of functions where you basically add the capital after. So you first add the capital and then you aggregate, whereas in this approach, you aggregate first and then allocate the capital. Yeah. That is an economic, let's say, different meaning of this thing. But most of the literature so far has only to look at this type of risk measures. Well, the price to pay in order to look at this, let's say, more meaningful economic interpretation is that you have somehow to work with multivariate functions. Yeah, here it's still a scalar function. It's just a regular scalar risk measure applied to an aggregated value. So it's not difficult. This seems, let's say, at the first look, a little bit more difficult. But one can also look at, let's say, scalar measures of systemic risk that are more of this nature. In the sense that I also, if I'm interested in, let's say, because this is like the overall amount of money to bail out a system. I could also look at the smallest overall amount of money that I sum up basically the regulations and look at the smallest possible sum of the regulations of the D banks. Yeah, would also give me a real valued risk measure, but it's not of this form, right? And what this is just, now I try the other pen if it has more power. Okay, if I have the set like this, maybe it's better, right? Is it better? So my risk measure, okay, not really. So my risk measure is a set, and a scalar version would be to basically scalarize into a certain direction, which would be direction 1, 1, 1, to get this point on my efficient frontier. And this point would be the smallest overall amount of capital. So it's also a real-valued risk measure, but it's a scalarization of these set-valued functions, basically. And has the advantage that it has a more meaningful economic interpretation with respect to regulation before the crisis happens, in contrast to be a bailout amount of money. And it also has a few more mathematical properties that are better in the sense. So we call this the insensitive approach, the classical one, because it's insensitive to the effect of regulation onto the system, whereas this one is sensitive to regulation. But mathematically, here in this case, you get a function that is translative again, so it has properties that are more similar to the regular risk measures, whereas this function is in general not a translative function, which makes a few more difficulties on a mathematical side as well. And this idea to doing this, let's say, allocating first and aggregating then, have also been looked at in two other papers. It's based on the same idea, but they also more looked at the, let's say, the scalarizations of it. But the basic idea was the same like in our paper, and the three of them appeared basically in the same time. Okay, so this was my first motivation, maybe to look at where multivariate problems in risk measurement appears. And we will later on also see a little bit how this is related to the dynamic problems that I will talk on in the second part of my talk. One more remark maybe on computing these sets, because in general people are always kind of scared of set-valued functions, but it's actually not so difficult to compute those. I mean, there are two possibilities. So the next chapter will just be a short remark on the computation of these sets. At the end, we are interested just in this kind of efficient frontier, right? The boundary of the set, because it's the smallest amount of capital that you need to add in order to make it acceptable. And there are two, in general, there are two versions on how you compute this. One is you can always kind of find a vector optimization problem behind this problem, such that this is basically the efficient frontier of this vector optimization problems. Yeah. So if you can solve a vector optimization, just think of the Markowitz problem. I think this is a picture everybody has in mind, where you have an efficient frontier. So so one could use this technique to compute the efficient frontier, basically of a vector optimization problem where you have several objectives. In this case of systemic risk, it's even simpler than that, because the computation, let's say if I go back a few slides, let's say in the Eisenberg-Noy framework, where was it here? We see that we are solving a problem where we have an upper and lower bound, which means we have a certain compact region where our risk measure will live in. That means we don't even need to compute. We're basically looking for this boundary, but we have a compact region where we know the set has to lie in, and we can concentrate on this compact region, which makes the problem really much easier. Because in this case, we can just use a very intuitive heuristic or algorithm to compute the set. One basically has, let me just go to the next picture. So we can put a grid on this compact region. So we're looking for the set. We don't know where the set is lying. We just put a grid on this compact regions, and for each grid point, and the grid point would correspond to a K1 and K2, yeah, the possible addition of capital for the banks, and we need to check for a given point K if lambda of x plus K is acceptable or not. So we just, for a given point, need to check acceptability, which is easy to do. And if let's say you start with a certain grid point, let's say this one, or you go along this line and you check for this one and this one, you can also use one of the features that, let's say you check this point and you saw it's not acceptable, which means it's not in the set. But then you also know that everything below here is also not in the set. Because of the monotonicity and the properties of our risk measure, the sets are always upward like this. Yeah. In the same way, if you check that this point is in the set, you also know the other points in the upper part that are in the set. So you actually just need to check some of the points, and then you move to the leftover points. You check this one, and you see, okay, these ones are then, you also know about them. Yeah. So you move to the ones that you haven't checked yet, but you solve also the problem for other grid points already. And this easy, let's say, grid search algorithm gives you basically an approximation. So at the end, you get an inner and an outer approximation of the set. You can either have a convex inner and outer approximation, or actually you get a little bit of finer approximation if you allow for this non-convexity. But it's very easy to compute these sets or an approximation of the sets. Yeah. In the systemic risk case, when you have this compact, let's say, feasible region. But even in general, as I said, you could use algorithms to compute vector optimization problems to approximately or compute these sets. So there are different options on how to do it. But we will also come back to this one later on a little bit. Okay, so this just as a comment about computation of these multivariate risk measures. I now want to come to the dynamic case, because this is where the dynamic programming will play a role. And the dynamic case is basically motivated. I mean, these set-valued risk measures appear also in other instances, also when you have transaction costs. So when you have, let's say, different currencies with transaction costs, you can also have these set-valued risk measures. So this is just one example. Systemic risk, which also leads to these multivariate risk measures. But then, if you think in the dynamic case, you basically have time 0 and time capital T. So until now, we just focused. Oh, okay. So until now, we just focused on a random vector at terminal time and the risk measure at time 0. Right? Which was just a static case. But now you might be interested in what happens when you have several time periods and your risk measure, let's say, until now we just looked at the set, the multivariate risk measure at time 0, but now you might be moving over time and you're interested in your risk measure also at later time points. Yeah? And so tomorrow's risk measure and the day after and so on. And these multivariate risk measures in dynamic time, the dynamic case has been studied by me and my former PhD student, Zach Feinstein. And so again, we get the set-valued function where the input is a random vector and the output is now a set of random vectors, like in this example, just in the dynamic case. And we want to have regular properties that we know for risk measures in general, normalization. So the risk of 0 shouldn't change anything. We have this translation property. If I add a vector to X, it should reduce the risk measure by exactly this amount. Monotonicity, which we also know from the scalar case. If something is larger or equal to another random vector, then the risk of this larger quantity should be smaller. And smaller risk just means that I have a larger set, because a larger set would give me a smaller amount of initial capital, right? And convexity, which we want to have for the risk measure for diversification purposes. Okay, so you can define these set-valued risk measures with the usual properties. And what we discovered was, and this is why I wanted to talk about this time consistency issue, that there is a set-valued Bellman principle behind it, which I haven't seen anywhere before. I mean, Bellman's principle is something that is well known and it's used in a lot of different applications, but there is something in the multivariate case which seems to be in total analogy to the scalar Bellman principle. And I think this is something interesting, and I just want to give you a little bit a feeling of what is going on there. Yeah. So for the risk measures, we basically say, or we define a risk measure to be time consistent when at a certain time point tau, if you know that the risk of X is bigger than the risk for any, let's say, set of portfolios Y, and this holds, let's say, appear almost surely. And then also at an earlier time point, the risk of X has to be bigger. So this is like the definition in the scalar case. Yeah? You basically don't want to contradict yourself. If you know at time t something is more risky for sure, then you don't want to make a decision that you regret for sure at an earlier time point. Yeah? This is what the meaning behind this. You don't want to contradict yourself in the decision-making process. If you know for sure something is worse in the future, you don't want to invest in this, right? So you want to have a consistent decision today. And we were able to show, so this is in the past years, I've worked with Zach Feinstein on this. We could show that this multi-portfolio time consistency is equivalent to something that looks like a Bellman principle, but for set-valued functions. So, which means if you're looking at, or you're interested in computing this set RT of X. So let's say you're interested in computing, let's say your risk measure at this time point, starting from, X lives at terminal time. So basically computing this directly, yeah, from time t to time small t. It would be the same then to computing the risk measure at some intermediate time point tau. So let's say tau lives in between here. So you could first compute the risk measure at an intermediate time point and then apply your risk measure at time t of this intermediate value, which is now a set. And the risk measure of a set is just defined to be the risk measure for each element in the set. Yeah, so you take the union of the sets, where you take the union over all possible sets at R tau. So this is what the meaning of this is, just a more compact way of writing it. That means you compute first the set here, and then you use the set which you computed to compute the risk measure at time t. And the multi-portfolio time consistency just tells you that it doesn't matter to compute it directly or to compute it in a sequel, going backwards in time, which is like dynamic programming, but in this case for a set instead of a real valued function. Yeah. And this was something interesting to see that naturally in the dynamic case there is something like a set-valued Bellman principle appearing, and we have a lot of different characterizations of this time consistency. Yeah, also the other ones that you know, maybe in the scalar case. But the only thing I wanted to point out is this one, because it's recursiveness. I had the feeling that there is something more behind it, not just for the risk measures, but there might be something more general, like a dynamic programming principle, which might be interesting in itself. Okay, and computational-wise, we could show that the calculation of such a time-consistent risk measure is actually, also you can compute the set RT of X by solving backwards in time convex vector optimization problems. Which means you can also use this backward recursion, You can use this backward recursion similar as we know in dynamic programming, where we solve, let's say, an LP in each step backwards in time. But in this case, instead of solving an LP, you solve a vector optimization problem in each instant. But otherwise, it's the same principle somehow. Yeah, and this is why I said the computation of the set is related to solving vector optimization problems. Yeah, it's basically the efficient frontier of a vector optimization problem, and you solve basically backwards in time in each step convex or linear vector optimization problems, which helps to the calculation of these dynamic set-valued risk measures. So there's something behind it which is like set-valued dynamic programming, and the only difference is that instead of solving LPs in each step, you solve vector optimization problems. But there are algorithms to do so, and they can just be used backwards in time, basically. And for the risk measures, we discovered this. We studied this time consistency a lot. And this computational side was also just published this year. But there is something, I think there is something more behind it. And this is where I wanted to, let's say, lead the talk today into this direction, to see a bigger picture behind it. Yeah, this is why I don't go too much into details. I just want to give the overall ideas to see something more appearing, basically. Okay. So in order to do this, I will give a different example, but you see from the structure, it's pretty much related to what I just talked about. Yeah. Which is the Markowitz problem. Because now, if you think about, I mentioned this already, that these sets also appear when you look at vector optimization problems and you think of the efficient frontier of, for example, the Markowitz problem. Yeah. And I was interested in looking at the dynamic version of this problem and to see if I can use this backward recursions also on these type of problems. Yeah. And it turned out that this is actually the case, and I think this is a very interesting observation in a field that doesn't exist yet, yeah, which would be, let's say, dynamic vector optimization problems. So this is joint work with Gabriela Kovakova. She was my master student in Vienna, and now she started the PhD with me recently. So this topic was basically her master's thesis. Okay, let me recall for a second the dynamic programming in the scalar case, yeah, the Bellman principle. Usually you look, so you have now, let's say, a usual one-dimensional optimization problem, where you minimize some expected costs. Yeah, so we have a scalar function f, the cost at each time point, and we want to minimize the expected costs at a given time point t. Yeah, this is let's say you start at time 0, you have one big optimization problem and you're trying to find a strategy over time, but then you might also be interested in the problem at time t and also finding the optimal decisions at this later time point. So you have an optimization problem at each time point t, and your objective is always to minimize expected costs over the residual time periods, make decisions there. And you have some constraints, decision variables, and states, and so on. And we say that the problem like this satisfies Bellman's equation, or the Bellman principle, and the problem is called time consistent if this value function, yeah, and the value function is nothing else than just the value of the problem. Yeah. If the value function satisfies this backward recursion, that the value function at time t for a given initial capital X can be written as a composition of a one time period optimization problem plus the value function at time t plus 1. And this helps to compute, basically, if you are able to compute this one, then you just have to solve a one period problem in order to compute this one, and this will be the input for the next earlier time point optimization problem, right? This is Bellman, where you backwards in time solve each one period problem, basically. Okay, and we are interested if something similar also holds for our multivariate problems. Yeah? Okay, but here basically the input is the value function, which is basically the value of this minimum, yeah, that the minimum is attained, and this you call the value of the problem. Now, in our Markowitz problem, we now have two objective functions. Yeah, on one hand, you want to minimize or you want to maximize expected return, which is the same as minimizing the negative of the expected return, while you also want to minimize the risk of the return. Yeah, so you have two objectives, the expected return and the risk. In the classical problem, you would take variance, but later on, a lot of people used also other risk measures, yeah, coherent or convex risk measures instead of the variance. But you have basically two objectives. You want to minimize the risk and maximize the expected return, and then you have some constraints of self-financing trading and so on. But then what a lot of times people did, instead of solving this original, let's say, two-dimensional problem, you would, for example, bound the risk and just maximize expected return. Yeah? Which is nothing else than, instead of computing the whole frontier, you basically fix some expected return. I just reuse the same picture. So you fix some value m, and then you minimize basically in this direction and just compute this one point on the frontier. And if you vary the parameter m, you trace the whole frontier. Yeah. So this is a, let's say, usual approach to have a higher dimensional problem and turn into a one-dimensional problem. Right? Okay. But it's well known that this one-dimensional problem does not satisfy the Bellman principle. So it's not time consistent. That means in order to solve the dynamic Markowitz problem, you cannot use this you don't have this backward recursion. Yeah, it just doesn't satisfy this recursive representation, so you cannot make the problem, chop it into this smaller, easier one-step problems. It's just not possible. And there has been a numerous amount of papers on how to solve this time inconsistent problem. But what turns out, and I think this is a really interesting observation, is that instead of turning the problem into a scalar problem, like it's always done in the literature, you could actually just look at the original higher dimensional problem. Yeah, instead of scalarizing, my idea was to consider the original vector optimization problem and try to find a Bellman principle for that. Instead of, I mean, the scalarized problem we know already doesn't satisfy Bellman, but what about the set, basically? Because the sets are of a similar structure like we know already from the risk measure side, so my hope was to get something there. But then, or why doesn't there exist already like a Bellman principle for vector optimization problem? It seems like a natural thing to do somehow. But if you think of having, I mean, in the scalar case, we know what we are interested in is actually this value function, right? The value of the optimization problem, because this is the one that scales, that recurses backwards in time. But if you think of a higher dimensional problem, it's actually not so clear what is the value of the problem. Yeah? Because the value of the problem, I don't know, you have an efficient frontier. So what is the value of the problem in higher dimensions? And this is something that is not so clear. Even if you take, I don't know, if you just write down, I think I have it actually on the slide. If you, for example, just take the minimum of two objectives, doesn't matter what it is, but for example, in the Markowitz problem, the minimum of two objectives. The minimum is really, it's nothing, it's just a symbol of saying we are looking for efficient points. Yeah? It's not the minimum in the classical sense. The minimum is the attainment of some infimum. Yeah? In the scalar case, it's well defined what the infimum is, and the minimum is an attained infimum. In the vector optimization problem, this is just a symbol that means we're actually looking for efficient points, right? That means the minimum itself is not a well-defined mathematical quantity that I could use as something for the value function. That means there is no natural value function, which means even to set up a Bellman principle for vector optimization is not as straightforward, yeah, in the classical sense. But what I was trying to do is to use a new approach that appeared just in the last few years, which is called, I mean, there has been a lot of research on set optimization. And you can always see vector optimization as a special case of a set optimization problem. Yeah. So here we have basically a function that is a vector valued function. For each input, I get a vector. But you could put, okay, let me just try to explain it a little bit. I know it's not an optimization talk here, but I think the idea you can pose. Let's say you have a vector function f. Yeah. For each x, it gives you a point. So for example, it gives you this point here. Yeah. You can turn it into a set-valued function by just adding your ordering cone to it. So let's say we are in R2 and our ordering cone is R2 plus. I can turn it into a set-valued function that is, instead of the point, I take the point plus a cone. Yeah. And then there's a theory about how to optimize set-valued functions, which tells me that the infimum or the minimization of a set-valued function. So if I take now, let's say the infimum over some set-valued function, so there's a theory that tells me that this is a closure of the union of all the points that are feasible. Yeah, so there is a well-defined minimum in the set-valued case. And a vector function I can turn into a set-valued function, and the infimum would then be the union of all possible points plus the cones to it. And the union of all these points would actually give me this whole set here, right? That means with this new theory of set optimization, which also applies to vector optimization, I suddenly have a definition for what a minimum of a vector function means. Yeah? The minimum would basically be the set where the boundary of the set is my efficient frontier. And this approach I try to use for our type of problem. So I used this new concept, which was, let's say, invented by Andreas Hamel and Andreas Löhne, and it's called the set approach to vector optimization problem. And then the value of the problem is nothing else than the upper image, and the upper image is the set that basically whose boundary is the efficient frontier. Yeah? So suddenly I have a definition of what the value would be. And this upper image, we have algorithms to compute it anyway. So in the linear case, so, I mean, this is just basically for definition purposes. So if I have, let's say, a matrix P, I have here several linear objectives and I have some constraints. I have my feasible set and the image of the feasible set. Then the upper image is nothing else than the image of the feasible set plus a cone. But it's exactly the set that I draw there already, yeah, whose boundary is the efficient frontier. This is a so-called upper image. But this is what the value of the problem would be. And it turns out that if I look, for example, at the dynamic Markowitz problem, I can prove that the value of the problem, which is this, yeah, the set, the efficient frontier plus everything above, is again of this recursive form. So it's the expectation and the risk of a point y and z, where y and z live in the upper image at time t plus 1. So I get again a recursive form of the value function if I consider the value function in this, let's say, new approach. Yeah? And if I compute the set, then this is nothing else than a one-period vector optimization problem where this is my constraint set. And if I use algorithms to compute the set, this is again the input for the next period's optimization problem. Yeah? So I can prove that the dynamic Markowitz problem is time consistent, but time consistent in this sense. Yeah? As a problem in 2 dimensions, but not as a problem in the scalarized case, which until now everybody was just looking at. Yeah? So I have something more, a theory, let's say, behind the problem, which makes it again easier, and I can use algorithms to compute backwards in time and solve my Markowitz problem. Yeah? So it is time consistent. I just need time consistence of the 2-dimensional problem. Yeah? And I think this is something that is very interesting, and until now I haven't seen anything in this direction. And I think it holds even more general. I mean, we just looked at the Markowitz problem, but it holds also for more general type of problems. So I think there is a new, let's say, theory developing of dynamic programming for high-dimensional problems. And we have seen, I mean, my applications now, the Markowitz problem, but also these multivariate risk measures are basically of this type. There's a lot of interesting applications where this might be of importance. Okay. So the vector optimization problem is time consistent, but the scalar problem is known since like 50 years that it's not time consistent. And as I said, this was basically the master's thesis of my student, Gabriella. We are now trying to turn it into a paper, and we also started to look at more, let's say, general type of problems, because you can actually see that this principle holds also not just for the Markowitz problem, but generally to look at convex vector optimization problems. As long as each component of the problem, here we have several objectives, if each component is basically of a scalar time-consistent risk measure type, like expectation or dynamic risk measures, things like this, then you get this recursion of the value function over time and can use this algorithmically. There's still a lot of open problems or scientific challenges, I should say. So there is still a lot of work in progress, but I think it's a very interesting topic in itself. And it's also related to some other work. So, I mean, we just looked at the discrete time because I just wanted to understand first, how this works, how do I compute it, and what is the setup. There's also some work related by people that are more looking at the continuous time case, like Jinma and Zheng. They just published last year a paper about dynamic approaches for some time inconsistent problems and continuous time, so they are more coming from the BSDE side. But I think the results that they have are pretty much related to our concept of time consistency. I mean, they are looking at scalar problems, but they're basically changing the scalarization over time, which is, I think, equivalent to what we are doing here with our set valued function. So I think there's also some connection, let's say, coming from other sides. But yeah, I mean, so there's still a lot to do to understand completely what's going on. But I think there's some related problems that are of the same type. Okay. So this just as, I think, the generic picture behind my set-valued risk measures and how this, I think, relates to something that could be a dynamic programming principle for multivariate problems. Thank you.
Questions?
Yes.
How many dimensions can you handle? Your grid search method looks difficult if you've got thousands of dimensions.
So, I mean, for the systemic risk measures, we basically have examples where we have large networks of 300 banks or even like 1,000 banks. For the computation, we usually group the banks into, let's say, big banks, intermediate banks, and small banks to have a grid that is like in 2 or 3 dimensions, and then it's pretty easy. If you would do it for the complete network, I mean, just the number of grid points would explode. Yeah? But I think the grouping already gives you a much more intuition than if you would just compute a scalar point. Because until now, everybody was just computing basically one point, and typically in the insensitive case, which is even basically with the not so good economic interpretation. So, I mean, of course, we cannot do wonders, so we cannot do it in high dimension, but the grouping gives you something that is reasonable enough to get much more information about the systemic risk than if you would just compute a single point, which until now was the state of the art. Yeah. But of course, in higher dimensions. But we have also one case study, which actually, I think a network of 1.8 million of banks, but the grouping is the part that makes it feasible. Yeah, so it's not the number of banks in the network, but if you group it, let's say, but I think this was also something that was interesting with respect to the first talk this morning, because we are grouping just by size. Yeah, but if you could make, and this is very much, I think he's not here anymore, but Patrick this morning was talking about how to actually find a good grouping of a network. So I think this could be something that could be very useful also in this case. And then, I mean, the Markowitz problem is just in 2 dimensions, so there we don't have any problem at all. The Markowitz problem is just expected return and risk. So this is 2-dimensional, so there algorithms work pretty well. For the vector optimization problems in general, if you are up to, let's say, 5 dimensions, these algorithms are quite fair. If you go higher, there are also some problems there.
Excuse me, when you're doing the dynamic version, at
Yes.
every point in the backward induction, you have to do this over random variables.
So we usually use like a recombining tree.
Okay.
And then at each node in the tree, you basically solve a vector optimization problem and use this as an input for the next time period.
Okay, so you're just using binomial tree and then going back.
Yeah, and for the Markowitz problem, so until now in the master thesis, we looked at the case where the risk measure is a coherent risk measure. And coherent risk measure just scales, right? You can take positive constants out. And this actually means that instead of each node, at each time period, you just need to solve one problem, and the others are scaled versions of it. So which really means, in this case, we're just solving backwards in time one vector optimization problem in each node. So computational, this is actually a very good thing. There are still open problems in general for the general case, which we are working on now. Because if you think about the scalar dynamic programming principle, you would actually usually analytically solve the problem, the one-step problem, and then just use it as a function of the little x. Yeah. And then you need to put in whatever x comes at this point, because we don't know it yet if we go backwards in time, right? And this is something which in higher dimension or vector optimization problems, if you're not in the coherent case, we cannot really solve because there are only algorithms to numerically solve it, but not to analytically solve it. But we have some ideas on how to overcome these problems, but it's a bigger, let's say, research project that is still in progress. So in this paper, we basically looked at the coherent case because this problem doesn't appear there. Yes?
When you're looking at the coherent case, so you assume that the problem is convex?
Yes, it's actually polyhedral. In the coherent case, you have basically a linear, either a linear vector optimization problem, so things are much easier, which means the set is actually not convex, but it's like a polyhedral set. And then you can exactly compute it instead of needing to approximate it.
So you're not going to look into moments like the paper by Dayball, the optimization, like higher moment coherent risk?
Well, we use a coherent risk measure. So the rho, instead of the variance, we basically use a conditional value at risk, or a coherent.
And you assume that it's convex or like convex?
It is convex, yeah. Yes. But it's also positive homogeneous, which is for the coherence important. And the more general case, convexity we will assume anyway. Yeah, but for the coherent risk measure, you want this positive homogeneity that you can take out constants. This is an assumption that is very useful here, but we are working on dropping that one. But convexity we will always assume.
Okay.
Because solving non-convex problems is actually a very different story. Yes?
It's more of a comment than a question. For the problem that you're looking at in the end, the Markowitz one, if your risk measure is low invariant, which is the case, for instance, if you take mean variance, then there is another way to make the problem time consistent. You enlarge the state space by adding the law of the process as a state variable. So it's infinite dimensional, and then you end up in this Makin-Vlasov type of problems. But at least in continuous time, there is a dynamic programming that works there immediately. Okay. You have some kind of AGB equation in the space of measure that's complicated. But you can do stuff over there. I was wondering if there is a link with this or not.
I don't actually know the result, so I would be happy if you can send me the reference. Yeah. But I know that there are a lot of, let's say, workarounds somehow to make the problem time consistent. But what we are doing, we're looking at the original problem, and it is already time consistent, so we don't have to make it time consistent. But I don't know. I have to look at the reference if there is something that is related to this.
Yeah, because being from mostly continuous time, when you show me dynamic programming, I want to see a PDE in the end. But
I think there is a link, but we haven't worked it out yet. But I think there's a link in the sense that if you would scalarize, you would have a scalar problem. But if you keep the scalarization constant over time, it's not time consistent. But I think if you move the scalarization over time, there exists a moving scalarization that is time consistent, and for those, an HGB will be available.
The approach of Mazang
yes,
and Kaman,
exactly.
The one I'm talking about is different.
Yeah, but this one I don't know. So
we can talk about it.
Yes.
Okay. If nothing else, let's go for coffee outside.